In today's video, we are going to look at an application of the Taylor expansion. In particular, we're going to apply the Taylor expansion to a specific function and calculate it step by step. In this first video, we're going to focus on a simple function, where f of x, the function that we're going to Taylor expand, is simply equal to e to the power of x. And what we're intuitively doing when we take a Taylor expansion, or we calculate the Taylor expansion, is that we are approximating this function, in this case e to the power of x, around x is equal to 0. So in general, for very small x. And we'll see that this is a very straightforward procedure, which you can just do step by step, each time adding terms and making the approximation more accurate. We'll be starting from the general formula for the Taylor expansion, which I've already written down. Now, if you're not familiar with this formula, I gladly refer you to my previous video where I cover each symbol in great detail. Now, the most notable thing that students find daunting is this thing right here in the enumerator. But this is just the nth derivative of our function filled in where x is equal to 0 right here. Now, since the Taylor expansion gives us a very large sum with a lot of terms, we can start collecting terms and write e to the power of x as a sum of different terms. And we can go through these terms for each n step by step. So let's just start with the first one, which is the term where n is equal to 0. In this case, we have this f0 of 0, which is in this case just the 0th derivative of e to the power of x, filled in x is equal to 0. We divide this by n factorial, so 0 factorial, and we multiply it by x to the power of 0. Now, since we know that the 0th derivative of a function is just the function itself, we get e to the power of x filled in x is equal to 0. This is another notation to signify this. We divide this by 0 factorial, which is just 1. And we multiply it by x to the power of 0, which is of course also just 1. Now, since we know that e to the power of x is equal to 0 is just 1, we find that we get 1 divided by 1 multiplied by 1, which is of course simply 1. And we already have our first approximation. Simply that e to the power of x is approximately 1 if x is very small. Now, we know of course that if x is equal to 0, then we get exactly 1. And this is called the 0th order approximation, or the 0th term of the Taylor expansion. We can do better by looking at the second term in our series. In this case, n is equal to 1. Here we just write, so the first derivative of our function filled in x is equal to 0. We divide by n factorial, which is simply 1 factorial, multiplied by x to the power of 1. In this case, since we know that the derivative of e to the power of x is equal to e to the power of x, a defining property of this function, we get again e to the power of x filled in x is equal to 0. This time we divide by 1 factorial, which is again 1. And we multiply by x to the power of 1, which is of course simply x. Since again we know that e to the power of 0 is 1, so we simply get 1 multiplied by x, which is of course simply x. And we already have our second term, x. Now, this means that if x is very small, e to the power of x can be approximated by 1 plus this very small number x. And again, this perfectly checks out if you fill in x is equal to 0. Then you simply get e to the power of 0 on the left-hand side. This x drops out and we do indeed get 1, because we know that e to the power of 0 has to be exactly 1. Now let's go to the third term in our series, which will be for n is equal to 2. Now we'll do this as a final explicit calculation and then try to extract the pattern that we find to get all of the other infinite terms. So we get in this case the second derivative of our function, again filled in x is equal to 0. We divide this by 2 factorial multiplied by x to the power of 2. Again, since the second derivative of e to the power of x is again e to the power of x, we get e to the power of x filled in x is equal to 0. And then we divide this by 2 factorial, and we multiply by x to the power of 2. In this case, we again get the enumerator e to the power of 0, which is equal to 1. So we get 1 divided by 2 factorial multiplied by x to the power of 2. So we can add our third term, which is 1 over 2 factorial multiplied by x to the power of 2. So let's now try to extract a pattern from these three terms already. I already mentioned a couple of times that the derivative of our function in this case is just our function itself. And this is of course because any derivative, so the nth derivative to x of our function e to the power of x will always be e to the power of x. It's this very defining characteristic of e to the power of x. This means that any derivative that we have to take in this series will always return e to the power of x. And since we always have to fill in x is equal to 0, this enumerator here will always be 1. And so it can always be dropped. What remains is this denominator, which is always the factorial of n, which was n is equal to 0, n is equal to 1, and n is equal to 2. And of course our power of x. In this case it was x to the power of 0, x to the power of 1, x to the power of 2, and so on. Thus we can see the following pattern that allows us to approximate e to the power of x, or in other words write down the Taylor expansion. We have that e to the power of x will be equal to the sum of x is equal to 0 to infinity of the following. We have this factorial in the denominator, 1 over n factorial, multiplied by x to the power of n. And this will be our Taylor expansion for e to the power of x. And it indeed checks out because we have explicitly calculated the first three terms. We have 1 plus x plus 1 over 2 factorial times x to the power of 2. However, we can now complete this series by simply writing down more terms. So we have that e to the power of x can be approximated or written as 1 plus x plus 1 over 2 factorial times x to the power of 2. These are the terms we already calculated, but we can now just go on. 1 over 3 factorial times x to the power of 3 plus 1 over 4 factorial times x to the power of 4 plus and so on, with each term adding to the accuracy of our approximation. And this equality sign here is only an exact equality sign when either x is equal to 0 or if we actually calculate all of the infinite terms. Now, since we cannot do this, we put this approximation sign above this equality sign. And that is how you calculate the Taylor expansion of e to the power of x. If you appreciate this video, consider giving it a thumbs up. And if you want to see more videos like this in the future, consider subscribing. And with that, I see you in the next one.